So hey everyone, this is Ayush, and in this video we will learn about segment tree. So segment tree is an range query data structure. It is used for performing range queries quickly, like to update an element within a particular range or to find the answer in a range L to R. We use segment tree. Before understanding the segment tree, I have divided this video in four parts. In first part, we will learn what is the need of segment tree. In second part, we will understand the working of segment tree. The third part is all about analyzing time and space complexity of different operations which we used to perform using in segment tree, like doing queries, range queries, performing updates, building a segment tree, and in last we will implement it. That is, we will code it simply. Okay, so let's first understand what is the need of segment tree. Because before understanding any concept, what I think, if we know the problem, then understanding solution feels better. Okay, so let's say I gave you this array and let me do zero-based indexing, and I ask you some queries of type L comma R, where I ask you to find the sum of elements in the range L to R. Now, the most brute force way to do this is to iterate from L to R and add all elements in your sum variable. For query 1 to 4, what you will do, you will simply iterate from index 1 to index 4 and add all these elements in your sum variable 5, 6, 7, 8, 9, 10, 11, 12, 13. Similarly, for query 2 to 5, we'll iterate over elements from index 2 to index 5, and the sum is 11 plus 8, 90. Now, the problem with this approach is, let's say the size of array is n, and if I give you q queries, then in worst case, your time complexity for each query will be n, and your overall time complexity will be q times n. Okay, because for each query, in worst case, you want to iterate over the n elements, and for q queries, it will be q times n. Now to optimize this, we have prefix sums. What are prefix sums? Let me write this array 215347, 215347. Okay, now we simply take prefix sum on this array, where prefix of I gives you the sum of elements from index 0 to index I. So you can see for zeroth index, prefix of 0 is 2. For first index, prefix of 1 is the sum of elements from zeroth index to that particular index. Here in this case, it is 1. So it will be 2 plus 1, 3. For prefix of 2, it will be 2 plus 1 plus 5, which is 8, and so on. Okay. So these are prefix sums. And using prefix sums, you will answer each query in big of 1, because you just have to use this simple formula that, let's say now I again ask you to find the sum in range 2 to 5. You cannot directly answer prefix of 5, because prefix of 5 has the sum of elements from 0th index till 5th index. But I ask you the sum of elements from 2nd index till 5th index. So in that case, we need to subtract the contribution of these two elements. Okay, and these two elements contribution need to remove. So usually we remove the contribution of elements till L minus 1. That's why our formula is prefix of R minus prefix of L minus 1, which you can see here, prefix of 5 minus prefix of 2 minus 1, 1. Okay, this will simply give you the sum of elements in the range 2 to 5. Now again, if I give you q queries, and each query now you will answer in big of 1, your overall time complexity will be q times 1, which is simply big of q. Okay, now everything looks fine till here, but now I will add the main problem, that let's say till here you was answering static queries. What are static queries? That the array was static. There were no updates on the array. The array was same from the start of all the queries until the end of all the queries. But let's say the queries are not static. Let's say I add updates in this queries that update the element at a particular index and then tell me the prefix sum in range L to R. Now, you cannot simply create prefix sum. You can, of course, you can create. You have to update the element. Let's say I ask you to update the element at fourth index. We have four, update it to eight. And now I ask you the sum of elements in 2 to 5. Yeah, now you can take prefix sums, but for creating the prefix array, you will need big O of n time. Okay, this will be the time complexity of creating the prefix array. And for Q queries, your time complexity will again become Q times n, because now you have to update the element and again you have to take the prefix sum. So in this case, your time complexity will become Q times n. Now here, segment tree helps us. We have to optimize this factor of n using a segment tree, because segment tree can update the element in log of n time. We will see the proof of this hidden video, that how segment tree update the element in log of n time complexity, and and it also answers our query in log of n time. So instead of n, if we use an segment tree, the time complexity will become q times log n. Okay, so this is the need of segment tree, that whenever you have updates and you have to perform queries, and for doing that your current time complexity is too expensive with respect to time with respect to constraints. Most of the times in on most of the coding platforms, this q will be 10 to the power 5 and n will also be 10 to the power 5. I'm not saying always, but in most of the cases. And this will result into 10 to the power 10, which we all know, which will not pass. We need something which is still 10 to the power 8 for 1 second time limit, which is standard in competitive programming or DSA. Okay. And one thing I want to mention is that it is not like that whenever we have updates and queries together and we want to optimize our time complexity, we will use segment tree, because this here we were talking about addition, and all functions won't behave like addition. In case of some functions, even if I don't give you updates and I just give queries like this that tell me this particular value in L to R, still you have to use a segment tree. And which functions are that? Maximum, minimum. Let's say I ask you to tell me the maximum in the range 2 to 5. Now, in this case, you need to iterate from 2 to 5 to find the minimum. You cannot create a prefix minimum. You can create a prefix minimum array, but you cannot use this formula for that. That we will take the minimum till fifth index and we will remove the minimum from this index. That is not possible, because minimum, maximum, GCD, this all are idempotent functions. Whereas addition and XOR are non-idempotent functions. Yeah, XOR also behaves like addition. In XOR also you can use this formula, but for idempotent functions you cannot use this formula. Now, what are idempotent and non-idempotent functions? On internet, you will see this equation about idempotent functions, that f of x equals to f of x. Now, you want to get anything from this, it simply means that the value of your function won't change if you keep putting same type of input or same input in that. Okay. For example, you can see here, if we have a, the max of a won't change if you keep putting the same input. Let's say max of a comma a will be a. It doesn't matter how many times you give a as an input, the value will always same. Let's say with a you give b and its max is c. Now it doesn't matter how many times you give b as an input, its max will be always c. Okay, similarly for minimum GCD. That's why these functions are said to be idempotent functions, whereas addition is not like these functions. If we have a and you give a as an input, you will get 2 times a. Okay. If you again add an a, it will becomes 3 times a. Now here value is changing. That's why addition is said to be a non-idempotent function. Although it is not that important for understanding segment tree, but I think let's mention this also. uh, we will need this concept in sparse table. When I will be explaining sparse tables, at that time we will need this concept of idempotent and non-idempotent functions. Okay, fine. I hope you guys understand. You guys get what is the need of a segment tree. Now let's understand the working of a segment tree. So I have taken the same array, and on this array I have already constructed a segment tree. I'm really sorry for this bad drawing. Actually, I am using mouse. I don't have pen and that stuff for drawing these things. This is the best which I can draw using the mouse. Okay, sorry for this, but I will give my best to understand, make you guys understand. Now, what is a segment tree? The formal definition of segment tree says segment tree is an binary tree data structure where your data is stored in leaf nodes and the intermediate node stores the value of a particular function in the range which that node denotes. For example, this node denotes range 2 to 3, and the value we have constructed this segment tree over addition function. Okay, and the value of addition in this range 2 to 3 is 8. As you can see, if you consider zero based indexing, 0, 1, 2, 3, 5 plus 3, 8. This node stores 8. Now I know you guys will get confused, like why this structure is like this, why data is stored in leaf nodes. I will answer you each and every doubt. Just stay with me. Now, one doubt will came in your mind that why segment tree is binary tree data structure? Why not a normal tree, an array tree? The reason is simple. The way segment tree is built and the way queries are processed inside a segment tree, its structure results in a binary tree. What is a binary tree? Binary tree is a type of tree where each node has at max two children. Your node can have max zero. It can keep zero children. It can have one children, or it can have two children, but not more than that. Okay. Now, why binary tree? You will get once I will explain how a segment tree is built. Okay, and why data is stored in leaf nodes. So let's first understand how a segment tree is built. So the length of our array is 7, and the first index is 0 and last index is 6. Okay. Okay. So let's understand how a segment tree is built. In this array, the first index is 0 and last index is 6. So we will start with this range. Initially, you start with a range. Okay. Now, forgot about this intermediate nodes, these values. I will explain everything. Now, what you do, you simply divide your range from the middle. Okay. And the formula for that is pretty simple. L plus R divided by 2. Using this, you find the mid. In this case, your mid will be 0 plus 6 divided by 2, 3. Okay. Your mid is 3. And what you do, you divide your range in two parts. One part will be from L to mid, that is 0 to 3, and second part is from mid plus 1 to R, that is 3 plus 1, 4, and R is 6. Okay, L till mid plus 1 and mid plus 1 to R. You divide your query like this. Now, why we divide our query like this? Everything I will explain while explaining you the times complexity. Okay, and so don't keep any doubt. Like I know a lot of students instantly get a doubt like why from middle, why not from any other point, why you're breaking query like this. Everything has a reason behind that. Please stay with me and just try to understand what I'm explaining. You will at by the end of video, I promise you that your all doubts will get clear. Okay, so once you divide your query from mid, don't stop here. Again, you have to keep your query dividing from the middle until your L and R doesn't get like it don't become equal. Okay, because once they get becomes equal, your middle will be always same. For 1 comma 1, your middle will be always 1. Okay, so we have to stop at that place. So again, you will divide your 0 plus 3 divided by 2. It will be 1. So let me write here. Your middle will be 2. So we will again divide arrange in two parts. One will be from L, which was 0 till mid, which is 2, and another will be mid plus 1 to R, which is 2 plus 1 3. Oh, sorry, sorry, my bad. Mid is not 2 in this case. Mid is not 2, mid is 1. 3 by 2 is 1. Sorry. I'm really sorry for this. Okay, so 0 comma 1 and 1 plus mid plus 1, that is 1 plus 1 2 comma 3. And similarly for this also, that 4 plus 6 divided by 2, that is 10 divided by 2 will be 5. So one call will be for 4 comma 5 and another will be for 5 plus 1 6 comma R 6, since here R was 6. Now you can see here our L and R become same. You will stop here, and what you will do, you will insert the value at that index, like 6 comma 6. At 6 index we have 6, so we insert a 6 in leaf node. That's why leaf node contains the data. This is the reason why leaf node contains the data, because at leaf nodes your L and R become same and we cannot further divide them. Due to that, since we cannot divide them, so our tree won't expand below it. That's why we put the values at ends. Okay. Now, similarly for this, you will divide it from middle. 4 plus 5, 9 divided by 2, 4. So L comma mid and mid plus 1 R, that is 4 plus 1, 5 comma 5. And similarly here, in 0 comma 0, 1 comma 1, 2 comma 2, 3 comma 3. Okay. I'm really sorry for bad handwriting. Okay. Once your L and R become same, just stop there and put the values at that particular index from the array inside the node. Like at 0 we were having 2, at 1 we have 1, okay, at 2 we have 5, at 3 we have 3, at 4 we have 4, at 5 we have 7, and at 6 we have 6. Now we will move from bottom to up. Since we will be on the leaf nodes, now we will move from bottom to up. Okay. Now your recursive call, of course, you can build segment tree using iterative way also, or recursive way also. But in this video, I will be explaining the recursive way because it's easy to understand, I think, as compared to even iterative is also simple, but for beginners, I think recursive is easy as compared to iterative way. Now, once your leaf nodes are filled, you have to fill the values of intermediate nodes. As you can see, here, we were having range 0 to 1, and from 0 to 1 we divide it from middle, and it goes like 0 comma 0 and 1 comma 1. Now you have to combine their values. Whatever value is at 0, whatever value is at 1, you have to combine them and you have to store in the node which is denoting the range 0 comma 1. Because here, as you can see, our range was 0 comma 0. At 0 comma 0 we have 2, at 1 comma 1 we have 1. But now I am asking you the sum from 0 to 1. So it will be the sum of 0 comma 0 and 1 comma 1 range, 2 plus 1 3. That's why this intermediate node is storing 3. Similarly here, at second index 2 comma 2 we have 5, at 3 comma 3 we have 3, but from 2 to 3 we will have 8. That is the sum of its two childs. Okay. Now again we will move back. We will again come to 0 comma 3, because from 0 comma 3 we break this segment in 0 comma 1 and 2 comma 3. Now it's time to merge these segments again. Are you getting what I'm saying? Earlier what we do, we break these segments. We break the 0 comma 3 segment in 0 comma and 2 comma 3. But now we will combine these segments because we have the answer. Earlier we were not having any answer for a segment 0 to 1 and 2 to 3. But since now we have the answer, so we will combine them. Because 0 comma 1, 2 comma 3 will result in 0 comma 3. So 8 plus 3, 11. And you can see 3, 2 plus 1, 3 plus 5, 8 plus 3, 11. So this node stores the sum 11. Similarly here, 4 comma 6 we divide into 4 comma 5 and 6 comma 6. Now, since both the ranges have the answer, we will simply combine them in 4 comma 6. So 11 comma 6, 17. That's why I have written 17 here. And you can see 4 plus 7, 11. 11 plus 6, 7. Okay. Similarly, 0, comma 6 we divide into 0, comma 3 and 4, comma 6. Now it's time to again combine them because 0, comma 3 and 4, 6 both have the answers. 0, comma 3 has answer 11, 4, comma 6 have answer 17. We combine them and store 28. And you can clearly see that the sum from 0 to 6 for the complete array sum is 28 because 6 plus 7, 13 plus 4, 17 plus 3, 20 plus 5, 25, 26, 27, 20. Okay, so in this segment tree is built. This is the initial first part because before querying the segment tree, we need to build a structure. So in this way, the structure is built. And I think now you guys will get the answer that why segment tree is a binary tree data structure. Because always we are dividing our query from middle. Okay, not query. I'm really sorry for the word query. We are dividing our range from the middle. Once we divide our range from the middle, we have two ranges. One range goes on left side, one range goes on right side. Sorry, ignore this word left and right. But we will be having only two ranges. That's why a node has only two childs. Okay, and it is same case for all other nodes also. On all nodes, we usually divide them from middle, and we are left with two ranges. So both the ranges acts as child nodes, and once they get their answer, we combine their answer and store in our current node. Okay, so this is why a segment tree is a binary data structure. I know still there will be one doubt that why we are dividing it from middle. That I explain when I will be explaining why the time complexity is log n. Okay. So I hope you guys will be clear with the building part of a segment tree. Now let's understand how updates are performed. Okay. Since we are done with building a segment tree, we have to solve the next problem for what we are learning the segment at how we will quickly perform the updates. Now, let's say I ask you to update the element at fifth index, change the 7 to um, change it to let's say 4. Okay, change the 7 to 4. Now, you guys may have in your mind that now again we have to construct this complete data structure from scratch. No, you don't have to construct this structure again from scratch, like start from 0, comma 6, then divide it in two parts, then divide this range in two parts, this range in parts. No, if we build it from scratch, then there's not learning the segment tree because in perfect sums also we were doing the same part that once an element changes, we were building perfect sums again. But here you don't have to build this structure again from scratch. You just have to change the values at some nodes. How? I will be explain. I will explain now. Start with your range. Let me remove this. Okay. So start with your range 0, comma 6. Okay. Why 0, comma 6? Because we will be start from root node. Na? Segment is in rotate tree, and we have if we have to traverse it, we have to start from root node. Of course, you can start from any node, but still understand. Like, see, I'm not explaining this basic stuff like prefix sums and binary tree in that depth because if I keep explaining this things in detail, then this video will become too much long. Okay, this video will become too much long, so keep it small and concise. I'm just telling this side concepts from a higher level. If you guys want to learn them, you can simply Google them or you can learn them from YouTube also. Okay, so you will start from 0, comma 6 and our target index is 5. We have to update the element at fifth index. We'll find the middle. I'm denoting middle from with m. So middle of 0, comma 6 is 0 plus 6 divided by 2, 3. Okay, now compare your target index with this middle element. Our target t is 5. Is my 5 greater than 3? Yes, 5 is greater than 3. Now, since your 5 is greater than 3, tell me in which part you will move. Because left part has the always has the range L to mid, and the right part always has the range mid plus 1 to R. and our target index T is greater than mid. So of course, the element which we have to update can't exist in left side because left side has only L2 mid. Okay, but my target index is greater than this mid. It means we have to move in right part. So from this node, we will go to this node. That is mid plus 1 R 4 comma 6. Okay, now we have 4 comma 6. Again find the middle. 4 comma 6 divided by 2. 10 comma 2 5. Now again compare. Is my target did my target exist in left range or right range? Okay, if your target is greater than mid, it means it is in right range. If it is equal to or less than mid, it means it is in left range. Now, since our target index is 5 and our mid is also 5, so our target index exists in the range L to mid. And as we know in segment tree, L to mid is on the left side of our current node. So from this node, we will come to this node, 4, 5. Once we are on 4, 5, again you have to repeat same process, 4, 5, find the middle. Your middle will be 4. Now again, compare your target element with our mid. Since our mid is 4, in this case, is my target element less than or equals to mid? No. We have two ranges. On left, we have 4, 4. On right, we have 5, 5. Is my target element in left range? For to have it in left range, it must exist in the range L to mid. But no, my target is greater than mid. It is 5. It means it exists in right range. So from 11, we will go to this particular node. And as you can see, we reach our target node 5, 5. Here we have 7. Now we have to update this 7 to 4. Okay. I'm writing a 4 here. Now, uh, just don't exit from here. We have to update the corresponding nodes also. Because just think, if this 7 changes to 4, which nodes will we have to change? This 11 has this 5, we have to change this 11. This 17 has this 5, we have to change this 17. This 28 has this 5's contribution, we have to change this 28. Okay, that means we have to update these 4 nodes. So that's why I said we don't need to construct this segment tree from the scratch again. We just have to change the values of some node. Because it's common sense, no? This nodes has zero effect because of change in fifth index. Because you can see they are denoting different ranges. Even this 4, 4 also has this 4, 4 also not contain the contribution of 5. But this ranges contains the contribution. So we need to update the nodes at that particular range. So once you update a 4, go back, and again perform the same procedure which we perform in build. What we do in build, we merge the answers from our left and right child. My left child is 4, right child is also 4. So this 11 will becomes 8. Again go back. Combine the answer from your left node and right node. My left node is 8. My right node is 6. So answer will not be 17. Now answer will be 14 for range 4 to 6. And you can see 6 plus 4 plus 4. 8 plus 6, 14. That's why 4 comma 6 is 14. And again at 28, combine the answer from left child and right child. 14 plus 11, which is 25. Okay. So in this way, we perform updates over a segment tree. Now, performing an update is results in a log n time complexity. Why? We will see ahead. So tell me, is it not better than prefix sum? In prefix sum, you have to update your complete array with a time complexity of big O of n. But now, you are just updating it with log n time complexity. So it's far better as compared to prefix sum. Okay. So this is how updates are performed over a segment tree. It becomes too messy. Let me remove this to explain you guys the last part, which is query. How we perform the query, which is the most important part. Okay, I hope you guys understand the update also. Now let's understand the query part. How queries are performed. We build the segment tree, we update the segment tree, but how we will answer the queries. Okay, now let's again take the same query which we encounter in past examples. That let's say I ask you to answer the sum of elements in a range 2 to 5. So, how you will find the answer for this particular range? Some of you may say that 2 comma 5 won't exist in segment tree. There is no way you can see 2 comma 5. Of course, there is no 2 comma 5. But see how we will find the answer for 2 comma 5. Again, start from the root node. At root node, you have to 0 comma 6. Find the mid. 0 plus 6 divided by 2, 3. Now we have two ranges 0 comma 3 and 4 comma 6. I hope you guys remember that formula that when we find mid, we divide ranges into part L comma mid and mid plus 1 comma R. Okay. Using this formula, we get these two ranges. Now, take any range. Let's first move to the left range 0 comma 3. Okay, my bad. I forgot to explain one thing that see when you are on a node. At first we were on the root node. First compare, is there overlap with your current range and this range? If there is no overlap, just get written from there. What is no overlap condition? Let's say this is your range 1 comma 8 and this is our another range 9 comma 11. There is no overlapping between them. If I draw a number line, although it's not necessary, I know it's very basic, but fine. If you have a range from 3 to 6 and I have a range from 8 to 10, are they overlapping? No, there is no overlap. Okay, fine. I will explain three types of overlaps out here. Actually, we will encounter three types of overlaps while answering the queries. First, there is a no overlap condition. When there is no overlap, there is no meaning of going downwards in a segment tree because your query is something different and your range is giving something different answer. Your query is from 8 to 10, but your range is from 3 to 6. So, although if you go down, you will divide this range from middle. It will, of course, not contain the answer. So, there is no point in going downwards, just return from there. Okay. If there is an overlap, there may be two types of overlap still. Either your both ranges may overlap partially. This is a partial overlap. Or they may overlap completely. This is a complete overlap. Okay. And okay, so there is a complete overlap. So I hope you understand these three types of overlapping. Using this, we will find the answer for our query. So when we were on root node 0, 6, check how your nodes, how your answer query or your question query, not answer query, your question query is overlapping with your range. Now there is a complete overlap between this. Now just tell me one thing. This 0, 6 has the answer of elements in the range 0 to 6. Okay, we discussed this earlier in build part. But we need the answer of the range 2 to 5. We need the answer in the range 2 to 5. Will it be good if I written this answer? No, because it had some extra answers. I think our array is 0, 1, 2, 3, 4, 5, 6. Yeah. There are three extra indices. Where it is? Okay. There are three extra indices 0, 1, and 6. We don't need them. We need only answer for this range. So whenever you have this type of overlap, what you have to do simply take your range, which was 0, 6, divide it from middle using this formula L, 1, mid plus 1, R, and then process these two ranges. Now you are on 0, 3. Now again check how they are overlapping. How they are overlapping. Now again in this case, this is our current range and we need answer from 2 to 5. They are again partially overlapping. We cannot return this answer. Okay. So now again what you have to do, you have to divide from middle. And if you divide it from middle, you will again get two ranges 0, 1, 2, 3. Now let's take the left one first, 0, 1. Now tell me one thing, how these ranges are overlapping? There is no overlap. There is not a single element which is overlapping. So what I explained or what I told earlier that if there is no overlap, just return. Don't do anything. Just return from that. Because 0, comma 1 don't have a single element from 2 to 5. So just return from there. Okay. You return a 0 from here. Now, let me explain here. We are here 0, comma 1. Yeah. You return a 0 from here. Now you are on 2, comma 3. Just tell me how 2, comma 3 is overlapping with our current range 2, comma 5. This is my 2 to 5, 2, 3, 4. Now, observe carefully. We have 2 to 3. We have the answer from 2 to 3. Yes, now we have a complete overlap. We have a complete overlap. Now in this case, we will return this answer. We return this answer. Now we have answer for this part, but still we need to find the answer for this part. From 2, comma 3, we will get 8. From here, we get 0. So from 0 to 3, from this range, we got 8 as a contribution in our question query. Since our query is from 2 to 5, and you can observe an array 0, 1, 2, 3. In 0 to 3, and my query is from 2 to 5, how much this range is contributing in my query? Only these two elements, 2 to 3, 8. That's why we got a 8 from here. Now let's process the right part. We haven't processed the right part. 4, comma 6. Now tell me how it is overlapping with 2, comma 5. Of course, there is a partial overlap. There is not a complete overlap. You will divide it from middle. Once you divide it from middle, you have two ranges 4, comma 5 and 6, comma 6. Now tell me one thing. This 6, comma 6 and 4, 2, comma 5 has zero overlap. So we will return an 0 from this side. And 4, comma 5 has a complete overlap with our range 2 to 5. We have already find answer for this part. We just need for this part and we get here 4, comma 5. Okay. It stores 11. So we will return this 11. 11 plus 0, 11. And we will again move upward and combine the answers from our left and right chain. 8 plus 11, 19. So this is the sum of elements in 2 to 5. And you can verify also 7 plus 4, 11 plus 3, 14 plus 5, 19. So in this way, queries are processed in segmentally. Okay. Let's take one more example. I think it may be unclear for some folks. Let's take one more query. So you guys will have more clear understanding for that. What happened to my undo? My undo is not working. Um, just give me a second. Okay. I think this is enough. Fine. Let's remove this also. Okay. Let's take another query. Uh, Earlier we took 2 to 5. Let's take 1 to 6. Let's take 1 to 6. And again, let's do the same procedure. Start from the root node 0, comma 6. And we have 1, comma 6. Now check how these ranges are overlapping. Although there is a complete overlap, I know there is a complete overlap, and as I said, if there is a complete overlap, just return the answer. But who is overlapping completely with whom? Our question query is completely overlapping with the current range. But the current range has answer from 0 to 6. The current range has answer stored from 0 to 6. But we need to find the answer from 1 to 6. Okay, so we cannot return this answer directly. So what we will do, simply break this from middle. If you divide it from middle, we will get two ranges using the formula L comma mid and mid plus 1 R, that is 0 comma 3 and 4 comma 6. Okay, let's process the right child first. Now tell me how 4 comma 6 is overlapping with our question query 1 comma 6. And I think now we have a complete overlap. Okay, we have a complete overlap. We want answer 1, 2, 3, 4, 5, 6. We want answer for all these indices and we got answer for 4 comma 6 for 4, 5, 6. So as we have the answer for 4 comma 6, we will simply return it. What is that? It is simply 17. Okay. Don't return it immediately. Let it store there. When we will arrive at this node after processing our left child, at that time we will combine the answer from left and right child. Okay. So we resolve this particular range. Now let's move with 0, comma 3. Now tell me how 0, comma 3 is overlapping with 1, comma 6. Of course, there's a partial overlap or complete overlap. But we don't want complete overlap. We want that our range must completely overlap with our question query. So we can directly return the answer. But here a question query is completely overlapping with our range. So because our this range contains the answer from 0 to 3, but we want the answer for 1 to 3. Okay. So what we will do? We will divide it from middle. Once you divide it from middle, you will again get two ranges 0, comma 1, 2, comma 3. Let's process the right range first. Now, as you can see, we need for we have the answer for 4, 5, 6. We want for the answer 2, comma 3. We will be here in segment 3. Since this is completely overlapping with our question query, we will simply return this 8. We will simply return this 8. Fine. So this range has also been resolved. Now let's process this 0, comma 1. Now, this 0, comma 1, we just need answer for now 1. We have find answer for all these indices, we need for 1. But 0, comma 1 has answer for twice, 0 and 1, but we need for 1. So what we will do? We will divide this 0, comma 1 from the middle. And once you divide it from middle, you will get two ranges, 0, comma 0, 1, comma 1. Let's process the left range first in this case. Once you go to 0, comma 0, you can see our range is 1 to 6, question query. Okay, but this range is 0, comma 0. We have no overlap, so we will return a 0 from here. Now let's process the right range 1, comma 1. Yes, 1, comma 1 is completely overlapping with 1, comma 6, and even we were just left with this one and we want answer for this. And what is the answer at first index? It is 1. So this 1 will return from here. Now let's move upward. Combine the answers from both the childs 0, comma 1, 1. So this 0, comma 1 range will contribute only this 1 in your question query 1 to 6. And as you can see, we don't want this 2, we just only want 1. Now this 1 and 8 will combine and will result into 9. Okay. And that you can see also in range 0 to 3, in this range, we just need these 3 elements from first index 5, 6, 7, 8, 9. And now we will combine this 9 and 17 together, which will result into 26. So the answer for the range 1 to 6 is 26. Okay. And since total sum is 28, we don't want this 2. So if you remove 2 from 28, our sum becomes 26. So in this way, we get the answer of our queries using a segment tree. Or you can say simply in this way, a segment tree works for answering our queries. Okay. So now let's move to the next part, which is understanding the time and space complexities of all the operations which we have performed. Okay. Okay. So now let's discuss the time complexities of all the operations which we saw. First, start with the space complexity. Now, the space complex of the segment tree is big of n. That is, there will be always at max n nodes. Actually, it's not n, since in big O notation, as we know that we ignore the constant. So after ignoring the constants, the space complexity comes out to be n, where n is your array size. Okay. I will show you in brief that what is the exact number of nodes we are required to build a segment tree. Now there are two scenarios of space complexity. One is for the perfect pass of 2 and another is for non-perfect pass. Let's understand first for the perfect pass of 2. Why? The reason is simple. Okay. And yeah, in this part also you will get the answer why segment trees and like is a binary tree data structure. Like as we saw the way we are dividing the queries, it results into binary tree, but why we are dividing the queries from middle, you will understand it in this time complexity part. Okay. Let's understand first space complexity. As we everyone know that segment tree is an complete binary tree. Okay. Segment tree is an complete binary tree. Really sorry for my words. Segment tree is an binary tree. Segment tree is an binary tree. Segment tree is an binary tree, not a complete binary tree. Now, what's a complete binary tree? A complete binary tree is that binary tree where All the nodes except the leaf nodes have two children. Let's see this. This isn't complete binary tree. Here, if you ignore the leaf nodes, all other nodes have two children. The root node have two children, the intermediate node have two children. Okay. Now, for a complete binary tree, there is a mathematical formula that if it has total n nodes, then the total number of nodes, sorry, if it has n leaf nodes, then the total number of nodes are, let's say leaf nodes are n dash, 2 times n dash minus 1. And you can see here 4 2s are 8 minus 1 7. We have 7 nodes here. 4, 5, 6, 7. Now, why a complete binary tree has 2 times n dash minus 1 nodes, where n dash are your number of leaf nodes? There's a proof for that also. It's a very simple mathematical proof. Just observe one thing. At each level, now in a binary tree, these are the levels. This is zeroth level or first level. This is second level. This is third level. At each level, you have some nodes. At first level, you have one node. At second level, you have two nodes. At third level, you have four nodes. And if you expand this, let's say, since we want a complete binary tree, here at this level, you have eight nodes. Can you observe one pattern? The number of nodes at each level are the powers of 2, 1, 2, 4, 8. So the total number of nodes are nothing but the summation of powers of 2 at each level. That's why, see, ignore one base indexing. We will do zero base indexing 0, 1, 2, and 3. This is 2 to the power 0. This is 2 to the power 1. This is 2 to the power 2, and this is 2 to the power 3. So 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3. Okay, now tell me one thing. This is in sequence. This is in sequence of elements. And this is not just a normal sequence of elements, it's an geometric progression GP, which we everyone have studied in our 11th or 12th standard GP. Now, if some of you don't remember what is a geometric progression, I will tell in short. Geometric progression is an mathematical sequence or a sequence of numbers 1, 2, 4, 8. This is our current geometric progression where your first term is denoted by A, your common factor is D. Now, what is this common factor? By multiplying this common factor, you get your next number in the sequence. For example, in this sequence, your common factor is 2. When you multiply 1 by 2, you will get 2. When you multiply this 2 by 2, you will get 4. When you multiply this 4 by 2, you will get 8, and so on. So D is your common factor. And let's say N are the total number of terms. Okay. It okay. So there's a mathematical formula for the summation of geometric progression, that summation of your geometric progression is A into d to the power n minus 1 divided by d minus 1. This is the formula. Let's plug in the values. S, that is total number of nodes. My A is 1 in our current sequence. D is 2. Now here we don't know the like n, so n minus 1 divided by d is 2 is 1. Okay. We don't know the total number of terms. In our case, total number of terms are nothing but levels, because those many levels we have, those many nodes we will have, and we want a summation. Let's solve this further. You will get 2 to the power n minus 1. Okay, but you guys will say we have 2 to the power n dash minus 1, and we are getting something like 2 to the power n minus 1. How they are related to each other. Now there's one more mathematical property for a complete binary tree. Now for this I don't have any proof, and I don't think so. It is necessary to give its proof that for a complete binary tree, listen carefully. For a complete binary tree, total number of leaf nodes are always total number of nodes, let's say capital N divided by 2. This is a mathematical property for complete binary tree. I don't have a proof. You can search it over internet, or you can simply draw complete binary trees and you can observe that for any complete binary tree, total number of nodes divided by 2 give you the leaf nodes, number of leaf nodes. Okay. Now, can we write this equation like this? 2 times 2 to the power n minus 1 minus 1. Okay. Now, what I said, 2 to the power n minus 1, okay, 2 to the power n minus 1 are your total number of nodes. Okay. Now, just tell me one thing. If you multiply this L, which is equals to n by 2, L by 2 are nothing but the total number of nodes. Okay. Because n by 2, this 2 will get cancelled and we will get the total number of nodes. And more thing you can observe here, if you multiply this 2 with this particular term, you are getting your total number of nodes. You are getting your total number of nodes. So, aren't these two terms correlated to each other? Can't I replace this 2 to the power n minus 1 with this n by 2? Of course I can replace. So once you replace that, you will get, oh wait, I think I messed up. Just give me a minute. Just give me a minute. I said something wrong. Just give me a minute. Okay, I'm really sorry. I'm really sorry for this thing. I mentioned one thing wrong, that total number of leaf nodes are not n by 2, they are n plus 1 by 2 in a complete binary tree. Okay, in a complete binary tree, the total number of leaf nodes are n plus 1 by 2, where n are the total number of nodes. And you can verify this formula over here. Total number of nodes here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And leaf nodes are 8. 8 plus, total number of nodes 15 plus 1 divided by 2. 16 divided by 2, 8. Okay, fine. So this is the formula for number of leaf nodes. First, I don't have any proof, I was saying. Now, just tell me one thing. We were here, we wrote this equation like this. Now, tell me one thing. When you multiply this term by 2 and subtract a 1 from it, you get total number of nodes. Correct? Similarly, if this term just multiplied by 2 and subtract a 1, what I am saying, n plus 1 by 2, multiply this term by 2. If you multiply it by 2, 2 will get cancelled and subtract a 1. This 1 will get cancelled. You are getting total number of nodes. You are getting total number of nodes. And to whom this term is equal? It is equal to number of leaf nodes. Okay, it is equal to number of leaf node. It means that in a complete binary tree, total number of nodes are nothing but 2 times, I denote it by L, but above I mentioned leaf nodes with n dash, is nothing but n dash minus 1. Okay, that's why in a complete binary tree, total number of nodes are 2 times n dash minus 1, where n dash are number of leaf nodes. I hope you guys get that. We wrote a GP, we wrote the summation of a GP formula. We get this equation. I wrote equation like this. I remove a power of 2. Earlier I was having uh, n powers of 2, and if I remove one power, I will be left with n minus 1 powers of 2. Okay, and this minus 1 was there by a formula. Then I put an equation in front of you that in a complete binary tree, the total number of nodes are nothing but n plus 1 by 2. Okay, n plus 1 by 2. And what I said, if I multiply this term by 2 and subtract a 1 from it, I get total number of nodes. Similarly, if we multiply this term by 2 and subtract a 1 from it, we get total number of nodes. It means this term and this term are same. So that's why I just replace it. Okay. Now, the thing is, uh, so if your size of an array is complete power of 2, you will at max need 2 times n minus 1 nodes. N is your size of array because in a segment tree, number of leaf nodes are equal to the number of elements in an array. That's why you will be using this number of nodes. And in big O notation, we usually ignore these terms. That's why we usually write it as big O of n. But some of you may caught me here and ask me, okay, Ayush, you told us for a complete power of 2, but what about those powers? Let me check whether it is recording. Yeah. Hmm. But what for those numbers which are not the power of 2? Correct? Correct. We need a formula for them also. Now tell me one thing. Let's say I took n. This n is not a power of 2. Let's say a power less than that is 2 to the power k minus 1, and a power just greater than that is 2 to the power k. Okay, is 2 to the power k. Now tell me one thing. If I multiply this 2, it will be equals to 2 to the power k. Similarly, if I gonna multiply this n by 2, it will be bigger than this 2 to the power k. This is basic maths. Okay. So let's write this inequality that of course this 2 to the power k is greater than n. But if you multiply this n by 2, it will be greater than this power. So let's write this equation like this that 2 to the power k is less than 2 times n. Okay, now let's write this equation in a better way. Let's assume, for example, in this 2's power, there are total n dash leaf nodes. Okay, if you construct a segment tree for this size array, there will be n dash leaf nodes. Now, what you can do simply, replace this 2 to the power k with n dash. We have n dash is less than 2 times n. Multiply this n dash, multiply on both sides by 2. We cannot multiply on only one side of 2 since we have to maintain this equality. We need to again multiply here by 2. Now subtract a 1 on this side. Also subtract a 1 on this side. Now observe what we get. We get 2 times n dash minus 1 is less than 2 to the 4 n minus 1. Tell me one thing. We saw this equation earlier. Here. What is this equation denoting? It is denoting the total number of nodes in a segment tree for a complete power of 2. So for this power of 2, we will have this many number of nodes. And it is less than 4 times n minus 1. It is less than 4 times n minus 1. Now, from this, tell me one thing. If, where, huh, if for this size of an array, we need this number of nodes, then of course, it's common sense that for this size of an array, definitely we're gonna need less number of nodes. We need the number of nodes which are less than this value. Okay, let's say for that we need total capital M number of nodes. So the capital M will be always less than this term because it's common sense no? That for this size to power of k, let's say this is 8, this is 16, this 12. For 16, if I need this many number of nodes, then for 12, which are less, which is a less size of an array, of course I will need less number of nodes for that. Okay. And tell me one thing, this 2 times n dash minus 1 is less than 4n minus 1. We have derived this equation from here. 4 times n minus 1. It means, and this, what is this n? This n is nothing but, here, this n is the size of our current array. It means if I build a segment tree for this size, the total number of nodes I will be required will be always less than 4n minus 1. Okay, that's why, see, this is an, I know for some people it feels unintuitive, but you have to accept the fact that for uh, huh, for a array size which is not a power of 2, you simply create a segment tree of 4n size. Remember this always. And not For this, we usually when we code no, we don't keep checking that the current size of an array is in power of 2 or not. We simply creates an array of this size. Okay, we simply creates an array of this size. This is an upper bound. This is an upper bound, as you see here. And as you know, we usually ignore the constants in a big O notation. Hence, the space complexity comes out to be big O of n. Okay, this video is a bit lengthy, but I wish I should explain all the things which at least I know at my level. Because when I was learning segmentary, I was not aware with all this stuff. I search over internet and learn these things, and then I come to know that okay, so that's why the space complexity is this. From where this all. So I wish you guys also know this stuff. So we are done with space complexity. Now, of course, if space complexity is big of n, time complexity of building a segment tree will also be big of n because you are building n nodes. Let me go to the previous slide. Since you are building n number of nodes, and tell me, what work we are doing on each node? You are going on each node, dividing it in two ranges and putting two recursive calls. One call is going here, one call is going here. And when they come back, you are just combining their answer using an plus or minimum or maximum, any function you can take. And these things happen in big of one. So on each node, you are doing big of one work. So for n nodes, n times big one, simply n. That's why for building a segment tree, you need big of n time. Again, I will explain on each node you are doing big of one work. You are not iterating over array or not doing something log n or n work. You're just dividing your segment in two parts and combining the answer on each node. It is simply big of dividing, like you are taking mid, let's say one, then you are putting two recursive call, one plus one for dividing from mid, one for left recursive call, one for right recursive call, one for combining their answer, big of four, which is simply big of one. This is for one node, and for all other nodes, it will be big O of n. So that's why the build time complexity of a segment tree comes out to be big O of n. Now let's understand this too. Point update and range query. The most important thing, like why we are using segment tree to optimize that prefix sums n factor to log n using point update and range query. Now here again we need some basic school level mathematics. Um, Let me erase this. Okay, now let's discuss the complexity of point updates. As we saw in the previous slide and previous part, how we were updating. Okay, how we were updating. We were finding the mid, we were comparing it with our target element. It's completely messed up. Okay, we were comparing it with target element and we were trying to reach to the leaf node to update that element. Now it can be any path. It can be this path. It can be this path. It can be any path. Okay. I wish my undo operation worked. It's not working. It's not working. Okay, leave it. Leave it. Now its time complexity is log n, where n are the number of nodes in a segment tree. How? Tell me one thing. As you guys learn in school, what log b to the base a denotes? This denotes how many powers of a are required to reach b. Correct? This denotes how many powers of a are required to reach b. Tell me one thing. What log of n to the base 2 will denote? How many powers of 2 are required to reach n? How many powers of 2 are required to reach n? Okay, so now tell me what this denotes. 16. As we know, 2 to the power 4 is 16. It means we need 4 powers of 2 to reach 16. We need 4 powers of 2 to reach 16. Can I say it like this? How many powers of 2 you are required to convert this 16 into 1? Or how many times you need to divide this 16 by 2 to get 1? Of course, you need to divide it 4 times because using 4 powers of 2, you have constructed this 16. So you have to remove all the 4 powers. So it means you have to divide it 4 times to reach 1. It means these two statements are interchangeable. That for any number n, how many times we need to divide it by 2 to reach 1 is nothing but log n to the base 2. Okay. Now I know, again, someone will ask, Ayush, this was a complete power of 2. What for the other, like, I have seen that log 2 10 is something, I think 3 point, um, log 2 10, 3.3 something. Okay. This is 3.3 something. So it means we need 3.3 operations. So we usually take ceiling value of this. You take ceiling value or we write a plus 1. That approximately 4 operations are required. But now someone will say, see this 10 by 2, you get a 5. 5 by 2, you get a 2. 2 by 2, you get a 1. So 10 to the 1 operation, 2 operation, 3 operation. Yeah, of course we need 3 operation, but not in every case. I will explain. Keep this aside for a time and keep this in mind. Now, similarly, tell me one thing. For any range L to R, how many times you can divide it by 2 so that it remain divisible? Now, remain divisible in the sense, how many times you can divide a range until and unless L and R are not equal. Till that you can divide them. Once they got equal, you cannot divide them further. So, how many times we can divide a range L to R? Of course, it is R minus L plus 1 log of 2 R minus L plus 1. Let's say your query is from 0 to n minus 1, that is for your complete array, and I'm considering this term equals to n. That's why your build time complexity comes out to be log n to the base 2. I know it's still confusing for some of the people. See, for those who are still confused with it, tell me one thing, what we are doing while we are updating an element. We are taking L and R, we are dividing them by 2, then we are left with two ranges L comma M, M plus 1 comma R. Based on our target element, we choose to with which range we need to continue, either with L comma M or either with M plus 1 comma R. On that basis, we are choosing with which we want to continue on the basis of T. Again, let's say we decide to continue with this. Divide it from mid. Like, see now, see, we are having L comma R, dividing it from middle. If your target element is somewhere here, you are proceeding with this part. Again, you have L to M. You are dividing it by 2 since your target element is here, and you are proceeding with this part. It's too big. This part, your target element is here. Again, you are dividing it from middle. Since your target element is on left side, you are proceeding with this part. Okay. Again, you divide it from middle. Since your target element is on right side, you reach here and you reach on your target element. Now, what you are doing? You are continuously dividing your range with by middle. You are dividing it by 2. And till what you can divide it by 2? Till what you can divide it by 2? Until it is not equals to 1. Now you guys may say, Ayush, that our range is becoming L comma L or something K comma K. It's not becoming 1. I know it's not becoming 1, but both have same meaning. Both have completely same meaning. To explain that, see, I will take 1 comma 10, divide it from middle. You will get 1 comma 5, 6 comma 10. Divide this again from middle. You will get 1 comma 2, 3 comma 5, divide it from middle. 6 comma 10 plus 6, 16 divided by 2, 8, and 9 comma 10. Okay. Now again divide these ranges from middle. If you divide this from middle, you will get 1 comma 1, 2 comma 2, 3 comma 4, 5 comma 5, 6 comma 7, 8 comma 8, 9 comma 9, 10 comma 10. And you have to divide these ranges furthermore for 3 comma 3, 4 comma 4, and similarly for them. Now how many levels were required? We were having 1 comma 10, then this 2, this. Total, we divide these ranges 4 times. 4 times. Okay. Technically, most of the ranges ended at third time, but for some we need to divide them 4 times. Similarly, for 10, as I explained, you divide by 2, you will get an 5, divided by 2, you will get an 2, you divide it by 2, you will get an 1. You divide it 3 times. But as I told earlier, for non-powers of 2, you have to take the ceiling value, which will comes out to be 4. And you can see here, we divide this range at max 4 times. You cannot divide it more than 4 times. Okay, that's why for numbers like 10, which are not the power of 2, we consider this formula, or you can say this. And for normal powers of 2, you can simply write log n to the base 2. This seems confusing when you will listen first time. What I say, what I wish, just rewind back the video and watch again. I 100% assure that you will understand it. First time, even I was confused with this, but when you will see this 2, 3 times, you will definitely understand what is happening. Okay, all from basics. That what this equation denotes, what is the meaning of this equation, or how many times we can divide a number by 2 to reach 1. Similar analogy we use for our range, how many times a range we can divide by 2 so that it we can divide it or it won't become equals to 1. Then we did a dry run on a range 1 to 10 to show you guys that although we don't reach 1, but reaching this terms is equally similar to reaching 1. This reaching from 10 to 1 is similar reaching 10 to this terms. Okay, that's why we need same number of steps now. In 10 also you gonna require 4 steps. Like if you divide it like this by taking ceiling value 10 by 2, 5. 5 by 2 is 2.5, ceiling value is 3. 3 by 2 is 1.5, ceiling value is 2. 2 by 2, 1. 1, 2, 3, 4. Now we need 4 steps. I hope you guys understand this part. Now let's understand the last part of range query. This is the most difficult part for me to explain just because to explain this part I don't have any mathematical proof. Even I read a lot of blogs on internet for the proof of that, but I didn't find any blog which explains that why range query is log n. But when I was learning a segment tree, um, so at that time my tutor taught me how this comes log n using an observation. Yeah, so now I'm sure drawing some stuff to show you guys how this comes out to be log n. Actually, it's not log n. More precisely, it's 4 times log of n. Okay. In worst case, it goes this, but in big O notation, we don't ignore this constants. Sorry, we ignore this constants. That's why we write log n. Now, I first tell me one thing. Ignore this 4. Actually, I need to give you proof for this 4. That is the hard thing. Explaining this part is pretty simple. It's very easy because as you guys see, did you guys observe one thing that the height of your segment tree will always be log of n to the base 2? Because as I told earlier, for any number, how many times you can divide it by 2? You can divide it this many times. So for range 0 to 6, or sorry, not 0 to 6, I'm still in that example, 0 to n, how many times this range can be divided by 2? Of course, this range is divisible only this many times. At when we are dividing it, we are adding an extra node in bottom direction. We are increasing our segment trees height by 1. So if you are if you are dividing your number this many times, it means you are adding this many terms in this many nodes in your segment tree in bottom direction. It means that is the height of your segment tree. Okay, what is height? Height is nothing but maximum distance which you can travel from a root node till leaf node. In this case, height is 3. 1, 2, 3. Okay, maximum distance, not distance, maximum distance, because here distance is 2 from root to leaf, but we consider maximum distance as the height of your tree. So if this is your height, and as we saw in query part, that tell me one thing, how deep you will go in worst case. You will go till leaf node to find your answer. You will go till leaf node. And what is the depth of each leaf node? The depth of each leaf node is log n to the base 2. Okay. So it means the time complexity of querying is simply log n, because in worst case you will go log n times down. Na? And tell me one thing, in each query what you are doing? You are just adding your ranges. You are just performing addition, and it's a constant time operation. So on each node you are performing addition, and you will travel log n nodes, like to be precise 2 times log n, because 1, 2, 3, and again you will go backward. But since we ignore constants, and on each node, since you are doing constant time of work, that's why your time complexity comes out to be n times log n. Okay, but I will not leave you guys here. The thing is, the thing is, if you guys observe, we are not dealing with only one range. Like, see here, if you have 1 comma 8, you have 1 comma 4, 5 comma 8. What I tell earlier, for one range, it is log n. But at one, we are dealing with lot of ranges, not lot of ranges, but we are dealing with pretty much ranges at a time. 1 comma 4 you will divide it from middle, 1 comma 2, 3 comma 4, 5 comma 6, 7 comma 8. For one range I tell log of n. Some of you will ask, what about other ranges? Now what I'm saying, combining for all ranges, the time complexity in worst case comes out to be 4 times log n. Now you guys will say, why 4 only? Range can be divided any times. Let's say you take 1 by 100. There will be a lot of smaller ranges at bottom. Why 4 times log 100 to the base 2 for that? Let me draw something for you so you guys will understand. Okay. Um, okay. Actually, I learned this thing from Priyansh Agarwal. If you are doing competitive programming, of course, you know who is him. Okay. This is my range. Let's say 1 till 10. Let's consider 10. 1, 5, 6, 10. 1, 2, 3, 5, 6, 8, 9, 10, and I'm not numbering at bottom. Now see, what I'm saying, any range you are processing in a segment tree will get break at max 4 times. It won't get break more than 4 times. It will only get break 4 times. The reason is very simple. Just observe what I'm doing here and tell me one thing. Okay. Let's say your array size is 10 and we have a pretty large query. Let's say this is your query range. Okay. And huh, sorry, sorry for this. And let's say this is your query range. What you will do, you will simply divide from middle. You know how we process queries in a segment tree. We divide them from middle. Once you divide them from middle, just see what is happening. This part acts as a suffix and this part acts as a prefix. If you are getting confused with this prefix suffix terms, ignore them. But then we have this part and part. Okay. We have this part and this part. Now, just tell me one thing carefully. We have to process now this range and we have to process this range. Still, they are partially overlapping. 1 to 5 store the answer for 1 to 5. But we want for something, let's say 2 to 5 answer. Okay. So we cannot return the answer from this node directly. So what you will do simply, you will divide it from middle. When you will divide it from middle now, can you observe one thing? At bottom, you will be processing this particular range. At bottom, at bottom, you will be processing this range and this range, one from here to here. And you can clearly see that this part was already completely overlapping with this part, but we were with this segment at that moment, so we were not able to answer directly. But once this segment becomes separate from us, we were left with this part. It was completely overlapping, but we cannot return its answer directly from here. So you return its answer from here. And for this segment, you will again process similarly from here, that you will divide from middle. Again, you will be left with two segments, and those two segments you will left with four segments. But out of that four, similarly here also, this segment and this segment will not further get divided because they were already overlapping completely. Let me explain again. Let me explain again. Let me explain again this thing. Let me remove these numbers also. Forgot about these numbers and just focus on this diagram. Just focus on this diagram. Let's say this was the query, our range query. Okay. Now, since this is not, we got written the answer directly from this level, we will divide it from middle. Now you will be left with these two ranges once you divide it from middle. Now what I'm saying, once you divide this range into this into, further it won't get divided. As I told earlier, we have 4 times log n. A range will get divided at max into 4 ranges. Further that it will never get divided. The reason you can simply observe now from here. Just observe carefully. Just observe carefully. What we have did here. We have divided this range in two parts. This is our array range. Yeah? This is our query range. This is our array range. We have divided from middle in these two parts. And now we have this our query range. What we will do, we will divide it from its middle. Now, although the middles, you can see, okay, wait. Sorry, I'm really sorry. While processing queries, we usually don't divide our range, query range by two. We divide arrays range by two. I'm really sorry for this. So we divide our array range into two parts. Now, tell me one thing. The right part is already overlapping with our query, but this left part is not overlapping. That's why we will again this divide this range in two parts, array range. Once you divide it in two parts, tell me one thing, what this part will completely overlap with our query range. As I explain here, how query works in a segment tree, whenever there is a complete overlap, we returns the answer. Let's say your 2 comma 3, your question queries from 1 to 10, and your 2 comma 3. 2 comma 3 is completely overlapping with your question query, and it's contributing it in it. So we return answer directly. Similarly here, as you can see, this question query was not completely overlapping. This array range was not completely overlapping with the question query. That's why we divide it from middle in these two parts. But you can see if you see the part from its middle, it was already completely overlapping with our question query. So that's why whenever you divide your query array range in two parts, not query, the right part always completely overlap with your query, and you simply return that. Here also same thing will happen, that okay, let's say ignore this. Here same thing will happen, although your array range is not completely overlapping with a question query. But just observe the part from middle. It is completely overlapping. That's why when you divide our array range from middle, this part completely overlaps with it and you return the answer for it. And this part still won't completely overlap. Okay. So we proceed them similarly as we proceed this range. Again, it will get divided into two ranges. Again, they will get divided into four ranges. Then we'll directly return the answer. And again, this two will process. So in this way, a query can at max get divided into four different queries. That's why it is said that the time complexity for a range query is said to be 4 times log n. Okay. Still one last time I'm explaining this. Third time I'm explaining this. I know it's way confusing to understand. The last time I'm explaining. One more last time. Let's say you have this your range. Why it's not undoing? Okay. Let's have this is your array range and this is your query range. Array. Query range is from this to this. Your array range is not completely overlapping with your query range. Hence, you divide your array range from middle. Okay, your query is still like this. Hmm, Your query is still like this. You divide your array range from middle. Okay. Now, again, as you can see, your array range is still partially or not completely overlapping with your query range. Again, you divide your array range in two parts. Now, observe one thing. This is the middle of your array range. Can't you see the right part of the middle is completely overlapping with your R query range? Yes, it was overlapping. That's why when you divide it in two parts, just one part is solved forward. This part's answer is written in big of n time. Similarly for here, when you divide this array middle, the left part was already quickly overlapping with our query. Our array range is left range from the middle or already overlapping completely with our query range. Hence, for the left part, we return the answer, but for the right part, we process it. So as you see, our array range, or we at max go till four ranges, but when we are with four ranges, two of them always get cancelled, and we only process two of them ahead. Okay. So again, this two will break into two, and this will create four. Again, this will get cancelled and we process this 2 only till bottom. And as we know, it is log n. At max, we are can process 4 queries at a time. That's why the time complexity is said to be 4 times log n. As you guys observe that a range cannot get break more than 4 times. So at max, we will process only 4 ranges. Okay, but in big O notation we ignore constant. That's why the range query time complexity is log n. That's it. So this is all about the analysis of time and space complexity. Now let's move to the last part of this video. I okay. So now we will be coding a segment tree, and after that we will be solving questions. I have decided to solve the questions from CSES. We will be solving most of the questions from CSES range query section. Even I will teach the sparse table and Fenwick also. Now for coding purpose, I will be using Java. Although I have done competitive programming from last 3 years in C++, I has always used C++ for a CPDSA. But the reason I will be coding in Java is that most of the CP resources or DSA resources are available in C++. According to me, at least I observe that most of the resources are in C++. Even most of my friends who used to code in Java struggles. Like at one level, language doesn't matter if you're logic developed. The language doesn't matter in language you are coding, but still, most of it is in C++. So that's why I think if we put some resources from my side, it will be in Java. But still in description, you guys will get C++ code for this. Okay. Okay. So let's move to the last part, which is implementation. Now we will simply implement all the concepts which we have seen till now in the code. And before implementing it, I would like to mention one thing, that I didn't tell you that why we are dividing query from middle. As I told you, like I show you why the segment tree structure comes out to be a binary tree data structure. Okay, but I didn't tell you why we are dividing the queries from the middle. Its answer is very simple. Why we are using segment tree? Let me see whether it is recording or it is recording. Why we are using segment tree? We are using segment tree to optimize our queries, to optimize our updates. Okay, we are using it to reduce the time complexity. Now the thing is, to optimize the time complexity, okay, if you have a range, when you divide it from middle, now as I show you mathematically, we can divide it in at max this steps. Okay, we can divide it in at max this steps. Because of only this reason, we process the queries in segment tree like this, that we divide them from middle, and because of that its structure comes out to be a binary tree, like a binary tree. This is the reason why we process queries like this, because now tomorrow someone gonna ask me that what if I divide it from here? Yeah, you can do it. You will be left with something L comma K and K plus 1 comma R. Okay, but now this will not result in log of len comma 2 time complexity overall. It will be greater than that, because we are not dividing from middle, we are dividing from ends, and these lengths are variable now. But earlier when we were dividing from middle, we were getting let's say length is n by 2 parts. Again we divide them, we get n by 4, and as we keep dividing, we reach 1 at some moment. And how many steps required? This much. So because of this reason, in segment tree, okay, so because of this reason, in segment tree, we divide queries from middle, and because of that its structure comes out to be like a binary tree, and in case of complete pass off to complete binary tree. Okay, now let's say we have this array 1, 8, 4, 10, and I have to construct a segment tree over it. How are we gonna construct this in code? Now if some of you have idea of a binary tree and you have implemented it, you guys have deal with objects in C++, pointers. Okay, like you will create an class or like node, in that you have some parameters. Then in C++ you put pointers like this, not like this, but just telling you put pointers. So a lot of people will ask, are we gonna implement these things in segmentary? No, we will not implement segmentary like this. Okay, we will construct a segmentary or a raw array. The reason is very simple. Whatever numerical functions you are dealing with, whether it may be an addition, subtraction, division, multiplication, GCD, whatever it may be, their results are numeric. It's integer, long, whatever it may be, it's a numeric value, and you can simply store it in an array. You can simply store it inside an array. Why there is need to create all those mess? But it's not mandatory that, like, it's not we always create an segmentary over an raw array. We will be always able to create an segmentary over an array. Sometimes it may happen that you need to create a class. Inside that you have to create you need to create a class with some 3-4 parameters, and instead of numeric value in that array, instead of integer array, you have to create the array of those objects. Because in some questions we have to deal with some more stuff. Okay, we will see those questions ahead while solving questions from CSES. Just telling that it's not necessary you will always implement a segmentary over and raw array. It may happen that we need to create a class and we have to store the data inside its object, and that object we have to store in this array. But at the end you're gonna store all the nodes inside an array. Now just ignore this formula. It's a simple formula, and focus here. What I'm telling, consider root node at first index. We will store the root node at the first index. For left node we will take a value just greater than that, and for 1 its just next number is 2. For it right, we will take a value greater than its left child number. For 2, the value which is just greater than that is 3. Okay, now again move to the leftmost child. We are moving level by level. First this level, then this level, then this level. We assign this root node as 1, left child as 2, right child as 3. Then again move to the next level. Once this level is over, move to the next level and start from the left side. 2, 3, 4, 5, 6, 7. As you can see, I have assigned numbers to each node. Why I assign these numbers? Because we should know at which index we have stored the value of this node. Root node at first index, leftmost child second, rightmost child at third. Then for the next level, leftmost child at fourth, the next child at fifth, the next child at sixth, and the last one at seventh. And not for just this, for every segmentary from now you will store nodes in this fashion. Now like a lot of people implement an segmentary in an zero based indexing also, but I have a habit from past 2 years to implement the segmentary over an 1 based array. Okay, so there is no any issue. Just you have to, like, instead of 4 times n minus 1, you have to create an array of size 4 times n. That's it. No any difference. And even in implementation you won't face any issues. Just there will be change in formula. I will show that how you will change these formulas for zero based indexing. Okay, now you guys understand how we gonna number these nodes? 1, 2, 3, 4, 5, 6, 7. If there are further nodes like this, 7, 8, 9, 10, 11, 12, 13, 14, 15. So in this manner we're gonna number the nodes of our segmentary always. Now once you number the nodes, how we will put these values inside an array in code? It's pretty simple. Now focus on these two formulas. For the left child, if you start, we will start with node 1. While doing transition, if your value is equals to node, for left child you will multiply it by 2, and for right child, on multiplying it by 2 you will just add 1 inside it. Let's understand this thing by doing a dry run. We start with value 1. Okay, let's do the indexing of our array 0, 1, 2, 3. 0 to 3 we have the range. Now we are building a segment tree. Remember what steps we follow while building a segment tree. We take the range and divide it from middle. If you divide it from middle, you will be left with two ranges, which is nothing but 0, 1 and 2, 3. Okay. Now from the root node you are moving to this now from the root node you are moving to this two nodes. Okay, and here we have our node value equals to 1. Currently we don't have value in a left and right child, so we will store nothing here. Once they have their values, we're gonna merge them and store here. Okay, so what I'm saying, for your left child, which is this 0, 1, just multiply the value of your node by 2. It's 1, multiply it by 2, it will becomes 2. Okay, so it will come at 2. And for the right child, multiply it by 2 and add an 1. So 1 into 2 plus 1 is 3. Okay, so for this we have 3. That's why I said 1, 2, 3. For this 1, for this 2, and for this we have here 3. Now let's say we are in this range 0, 1, and the value of node here is 2. Now again divide it from middle, you will be left with 0, 0 and 1, 1. Now again use the same formula. For left child, multiply your value of node by 2. 2 2s are 4, and for right child it will be 2 times node plus 1. 2 2s are 4 plus 1 5. Okay, as you can see, 4 5. Now let's process this range 2, 3. Divide it from middle, you will be left with 2, 2 and 3, 3. Here the value of a node is 3. Multiply the value of your node by 2 for left child. 3 2s are 6. As you can see here, 6 for this left one. And for the right one, multiply it by 2 and add an 1. 3 2s are 6 plus 1 7. So you can see we have 7. Okay, so I hope you guys understand why we have this formulas, because using these formulas we have this sequencing which I show you to store the elements. Okay, for zero based indexing I will explain in code. Now let's complete our dry run. We are on 3, 3. The value there is 10, so I will insert at 10 at 7th index. Okay, then my recursive call will come back from here to here. Let's say first it goes on right child, now it goes on left child, and here L and R will becomes equal, so we have 6th index. For this we will insert here the value 4. Okay, I insert here the value 4. As you can see, I insert 4, 10 at 6 and 7 index, and now my recursive call will come back. And as of now we have the answer in our left and right child. We have to combine them to find the answer for our current range. Here this node is denoting the range 2 to 3, so it will just combine the answer from 2 times node, that is left child, and 2 times node plus 1, that is right child. 6 plus 7 14, sorry, 4 plus 10 14. Okay, 4 plus 10 14. And what is the index of this node? For this it was 1, and this is a right child since 2 times 1 plus 3, so here we will store 14 simply. Okay, now let's process this ranges. Let's say we are on right child, L and R are equal, so it's time to store the value in the leaf node. That is this is the index which we have calculated in the array using this formula. For 1 we have 8 and its index is 5, so here we will store 8. Okay, then from here our recursive call will come back. Again we will put one recursive call over here, and here as you can see we have 0, 0. L and R again become same, and the index we calculated for it inside an segment tree array is 4. So at fourth index, we're gonna store the value 1. Once you store the 1, your value recursive call will come back, and since the left and right child has their values calculated, you have to combine them. So left child it is 8, right child is 9, 4 and 5th index. You have to combine the values of 4th and 5th index, 8 plus 1, 9. You have to store here 9. Now this recursive call will come back to the root node, and this recursive call will also come back to its root node. Since for now root node, its left and right child have the values already calculated, we will store them at the index to which root node is pointing. So for root node, we start from the first index, so we will store at first index, and the value is nothing but index 1 for left child, 1 times 2, 2, 9, 1 times 2 plus 1, 3 for the right child, 9 plus 4, 13. Why 20? 8 plus 1, 9. Sorry, 14 plus 9, 23. 9 plus 4, 14 plus 9, 23. Okay, as you can see, 23. So in this way, we store the values of our segment tree inside an array using this simple formulas and simple numbering. As you see, 1, 2, 3, 4, 5, 6, 7. Now for update also, as you guys know, if you have to update the value at, let's say, this particular index, second index, it's 4, and let's say I have to update it to 97. You know the update logic which we use in the previous part, that divide your range from middle, check it with the target index. If it is less than equals to middle, go to the left child. If it is greater than middle, go to the right child. Once you reach to the leaf node, you have to update this 4 to 97, okay, whose index will be 6, and then just you have to combine the answers. This 97, 6th and 7 index, 97 and 10 will result in 107, and the index for this node is 3. So here you're gonna, instead of 14, you're gonna store 103 in an array. Now again, since this node was contributing answer in this node, so we change the value of this node. Even this node was contributing the answer in this node, so we have to change the value for this node also. So we have to combine the answer from the left node and right node. For the left node, it won't change, it is 9. For left node, formula is 2 times node, that is 2 times 1, it is 2, it is 9. And for right node, it is 2 times 1, 2 times node plus 1, 2 times 1, 2 plus 1, 3, 107. 107 plus this 9, 116. Instead of 23, you will store here 116. Okay. And for query also, it is exactly similar. Okay, it is exactly similar. The values you will return using simply, if your array name is sect of node, this will be the value which you will be returning while querying, because sect is the array. This array, if you name sect, and node is the index, so of course at that index the value will be stored, so you have to just return it. Things will be more clear once we start coding it. So I think let's move to the code part. I will be using Java for coding, but for C++ users, I will put my GitHub repo in description, where you can find both Java and C++ code. Okay. So let's implement this code or this logic. So I will create a class segment tree. Now even in C++ users, you can simply create a global array like this. Then you can implement 3 functions: build, query, update. Okay, there is no need to create a class always, but for being a better practice, I am creating a class. Okay, so we need first the size of our array, which will be n, public int n, and public we need our sect tree array, which will be of type integer. I will name it sect tree, sgt in short form. Now let's create a constructor, public sect tree integer n, this dot n equals to n. Okay, even let's create the object of our array. sgt equals to new int. As I told, we will create the array of size 4 times n. Even I have proved this why it's 4 times n. Okay. So by default in Java, all the values will get initialized to 0. In C++, use a vector and its constructor. Fine. Now let's write the build function. The code is pretty easy. Code is damn easy. There is nothing hard in the code. I don't know why people says that segment tree has very long code. It's pretty hard. This that, but its code is damn easy. Let's first implement the build function. Public void build. Now here we will be needing 3 parameters, L and R, which will denote the range for our current node, and of course the index of our array, that is node, as I show you this node which will start from 1. Okay. Now what we will do simply for building, we usually calculate the mid. Integer mid equals to L plus R left shift by 1. Okay, let's write it in simple way. L plus R divided by 2. Once you calculate the mid, we will put 2 recursive calls. Let's say let me undo this. Okay. Currently we are at 0,3. We will calculate the mid and put 2 recursive calls, one for the left child, one for the right child. For the left child you will do 2 times node, and for the right child you will do 2 times node plus 1 to get the indexing 2 and 3 for them. So simply we will put a recursive call L comma mid comma 2 times node for the left child, and for the right child mid plus 1 comma R comma 2 times node plus 1. Okay. Once your both recursive calls came back after doing their work, you have to combine their answers to calculate the answer for your current node. So for that we will write a merge function, and we will pass node in that. Public void merge integer node. So node is denoting our current secondary node. It will combine the answers from left and right child, which will be 2 times node and 2 times node plus 1. So it will be sgt of 2 times node plus sgt of 2 times node plus 1. Okay. But what will be the base case? As we know, when L and R becomes equal, like 0, 0, when L and R becomes equal, you have to stop there, because you reach a leaf node and you insert the value from your array on that leaf node. So we will write the base case if L equals to R, sec tree of node equals to, okay, we forgot to pass or accept our array of L. Why array of L? Because your L and R becomes equal, 0, 0, and 0 is denoting the element which one is stored. Okay, then return. Okay, we need to pass array over here, Okay, so this is a build function. Should we test it, or let's complete the rest of the functions? Let's test it. So I will create a class, public class main, public static void main. Okay, so let's take the same array 1, 8, 4, 10. Integer arr equals to 1, 8, 4, 10. Okay, so integer n equals to 4. Let's create the object of our segment tree. sgt equals to new segment tree, and inside that we will pass the size of our array. Okay. And once the object is built, we will build our segment tree. Now we have to pass L and R. So my L is 0 over here, R is n minus 1, that is 3, because 0 1 2 3. Okay, our node will be 1. We will start with, as I told earlier, we will be doing 1 based indexing over sec3 array, and let's pass our array. That's it. Okay, so let's print the values. Let's print over here, must be less than, since it's a power of 2, there will be, it's 7 nodes, so less than equals to 7 plus I, s out, st of wherever. Okay, fine. Now let's run this code. Oh sorry, I used print ln. As you guys can see, we have the exact array which we built. Oh shit, wait, let me redo it. Redo is not available. Okay, no problem. Let's write it quickly. So for here, 1 2 4, at 4 we will insert 1, at 5 we will insert 8, at 6 we will insert 4, at 7 we will insert 10. This node index is 3, which will combine 6 and 7, that is 14. For this index is 2, it will combine 4 and 5, that is nothing but 8 plus 1 9. And for root node it will be 14 plus 9 23. So as you can see, 23 9 14 1 8 4 10, 23 9 14 1 8 4 10. So our build function is working correctly. Now let's write the update function. Public void update integer L, our array range, and node integer target index, and the value which we need to put over there. Okay, so in mid also what we do, we calculate the mid. Sorry, in update also what we do, we usually calculate the mid, and what I said earlier, we will compare our target index with mid. If my target index is less than equals to mid, we will simply put a recursive call for the left child. Okay, let's say our target index is 1, you calculate the mid for 0 to 3, it comes out to be 2. Okay, and your 1 is less than equals to mid, so it means you have to go in this direction, because as you know 1 is here. So update L comma R comma 2 times mid comma target index comma the value. Okay, else, oh, spelling mistake, else copy the same line over here, 2 times mid plus 1 for the right child, and here it will be mid for and here it will be R. Okay, mid plus 1. Okay, and at last, after, since as I told, if you update this node is contributing in this node and in this node, so for both of them you need to call the merge function to merge the values from left and right. So you will call the merge function over here, and you will pass your node, and the base case will be simple. As you know, if L and R become simple, we reach our target index. So SGT of don't write here target index. Okay, the target index is with respect to array. In SGT, for that particular node, we will have a particular index in our SGT array, which in this case is equal to node. equals to that value. Okay, and just return from there. Let's check whether it is working fine or not. sgt.update, not update, it's update. Okay, so 0, 3, 1. Let's say let's update this 8 to 7. So in that case, here we will be having 7 plus 1, here we will have 8, and this will be 22. So my target index is 1 and the value I want to put is 7. And let's again put things out here, not print and I just want print sgt off. Okay, what's wrong? Why the values didn't get updated? I think I messed up somewhere. Even here is 0. It shouldn't be equals to 0. We should have something like 22, 8, 14, or 8, 10. This was my target index. I build a segmentary over here. Okay, so this is the mistake. Fine, this thing's not correct, but my value didn't get updated. Why this is happening? So let's debug this code. L equals to R, sgt of node equals to my value, and I just return from the, I calculate the mid, I compare my target index with mid. So L mid 2 times not mid, it's 2 times node. So this is the way you should also debug your code. Just find the problem. As we saw, the problem was with update function because build function was working correctly. So just check that particular code line by line. Because a lot of people ask me how you guys debug your code in contest or during ICPC in such pressure situations. So whenever you encounter a bug or some weird result, just debug line by line. Now here I was we have already tested a build function, but if we didn't test it, I would first print the values after doing a build. If everything seems fine, then there's a problem in update function. So simply I'm gonna check the code line by line. If code seems correct for me, then I will put print lines at each position, like here after merging, to check how values are behaving. In this way we usually debug our code. So my update function is working correctly. Now let's write the last function, public int, return type of int, because we need to return the answer. Same integer L R, integer node, integer capital L and capital R will be our query range. Okay, this will be our array range and this will be our query range. Now again find the mid, L plus R divided by 2, and just pass them in your query function, L comma mid comma 2 times node comma L comma R. Similarly here, query mid plus 1 comma R comma 2 times node plus 1 comma capital L comma capital R. Now since the return type is int, we need to capture this is the output we will get from our left child, and this is what we will get from our right child. We just need to combine them and return left plus right. We will get something from our left child, we will get something from our right child. Sorry, here it is too much messy. Left and right, you have to combine it and you have to pass it for your parent code. Okay, now let's write the base case. First of all, there is a case of no overlap. If you guys remember, as I told while explaining the query part, if your query is not overlapping with the current range, let's say your small l is 1 and r is 4, but your l is something 8 and r is 10, there is no overlap. This range has 0 elements which are contributing in your answer, so just written from there. So how you can check that? Either this r can be here, your l r can exist over here, or let's say this is your l and r. Let me draw a number line. This is your l and r. It may happen that your l comma r is here, or it may happen that your l comma r is here. There are only these two cases of overlap, non-overlapping. It will never happen that there is any other case, then it will be counted in partial overlap or complete overlap. So there are only two conditions: if my capital L is greater than R, or if my capital R is greater than L. So if my R, this or this, not this both at the same time. Either it may be this or maybe this. Okay, or capital L is less than greater than no, I think like this. Okay, what to return in this case? What you will return? Of course, you are doing addition, and since this range is contributing 0, just return as 0. Now let's write a case for complete overlap. Let's say this is a number line, here is my L, here is my R. Now if your array range is doing a complete overlap with your query range here and here, you just return that answer, because you got the contribution of this part. You have to find for this part and this part, so you will return this. So how you will write this mathematically? Either your L is greater than equals to this L, and this R is less than equals to this capital R. So capital L is less than equals to L, and here it should not be OR, because there is only one case of complete overlap, which is this. Both conditions should be satisfied simultaneously. Capital R, return the value which is stored in that particular node. Okay, for example, if your query range is from 1 to 3 and you are over here which is denoting 2 comma 3, so 2 comma 3 is completely overlapping with 1 comma 3. Okay, so you will just return the answer from this node directly, and for this node its index we know. For root node 1, left child 2 times node, and for right child 2 times node plus 1, so 2 under 2 plus 1 3, so SGT of node. If it is not a no overlap case, if it is not a case of complete overlap, then it is a partial overlap. You have to find the mid, put recursive calls for left and right child, combine the answer and just return it to the parent. That is it. And this is the complete code for the segment tree. It's not too big, it's really very small code, just 50 lines. And since now I'm explaining this code to you, so it took me some time to code it, but usually during contest or while practicing, I simply code it within 5 to 6 minutes. It won't take much time once you practice this. I will suggest while practicing the questions, don't just copy paste it. Initially, what you should do, write the complete template from scratch, because if you don't write a complete template from scratch, it won't fit in your muscle memory. And still, it may happen that at this point also some people may have doubt. Those doubts will also get clear by implementing it again and again, because it has happened with me, with my peer group too, that some things are not clear in first time, but if you code them again and again, those things get clear in future. So that's why simply just code it while solving any question. Don't just copy paste the template to save your time. So let's check the query function now. sgt.query. Let's query for 2 comma 3. sgt.query. Let's query for 1 comma 3. Okay, we need to pass L 0 comma 3 comma 1 0 comma 3 comma 1. Okay, let's run the code. So 14 and 21 for 2 comma 3 14, 10 plus 4 14, and for 1 comma 3 14 plus 8 nothing but wait for 1 and 3 it must be 14 plus 8 is nothing but 22 plus 1 23, but it is printing, why is printing 21? 0 3 1 1 3, everything seems correct. What's wrong? Oh, okay, we have updated this value now. I have updated this 8 to 7, that's right. Okay, so this is how you will write your segment tree, and this is the complete code. I will put this code on my GitHub repo, and I will mention its link in description. Even I will mention the C++ code too. Okay. One thing I wanted to show that, see, this was for addition. Now some of you may ask me how to do this for minimum, maximum, GCD. What you have to do, just come here in your merge function and just change this thing, add here comma, and in Java we have the math class which has the static function min, .min. In C++ you can simply write in C++ you can directly write min of a comma b. That's simple. You have to just change one line. Some things you may even change, like this was a complete binary tree, but the thing is, what will happen when you will encounter an array of size C? It's good I get this thing now. Let's say your n is not a power of 2. You will be not using all the indices from your array. Till some point you will use indices, and after that you will be left with some vacant values. Okay, and let's say you are over here and you will combine some values. One will be from here and one will be from there, and these values are vacant. There is nothing at those values. In case of addition in Java, as we know, the default values by default are 0. Okay, but for maximum, minimum, GCD, those will change your result completely. If you have an 8 here and here you have 0, let's say, and if you combine answer from them, 2 times node plus 1, your minimum will be 0, but it must be 8 because your array is ending over here. These are the vacant values. So for that's why, according to function, you have to initialize your array. You can initialize it using a for loop, or in Java we have the arrays class which have the static function fill, using, let's import the class sgt, and with what you should fill it. Now it depends upon the question. If in question you know that your value won't exceed the maximum integer value, and now here we are taking minimum, so we will initialize it with a very large value, which is nothing but from integer class in Java you can take the max value. Okay, of course if you want to take minimum, we will initialize with a very large value, and if we want to take maximum, we will initialize with very small value. Okay, so you have a minimum over here. The changes, these are the changes which you have to remember according to the function in the question. So you have to change the constructor, you have to change the merge function. These things won't change, these things will also not change. Something will change here. Don't return in 0, as I told, return integer dot max value. Okay, integer dot max value, and rest of the things will be same. Fine. Now the minimum for 2 comma 3 should be 4, and for this it also be 4. Instead of 2 comma 3, let's do 0 comma 3. Or let's do one thing, let's remove this update line. Let's find an update for 2, 3. Put this line over here, and instead of 7 I will be putting -7. Okay, now let's execute this code. Okay, for this we are getting correct value, which is nothing but -7 for the complete array, because this which index, first index will get 8 will be replaced by -7. But why we are getting a garbage value over here? The reason is this: you have to change this also. Four comma 7. Okay, for max you have to just change this to max. Here you have to change the value, then change this function and change this. These are the changes you have to do according to your function which you will implement inside a segment tree. In case of object segment tree, let's say you have to store 3-4 parameters, just create a class, and instead of int just create that class object array over here and write your merge function according to that, and you are done with segment tree. Okay, so thank you for watching this complete video. If you guys have any doubt, you can comment. I will definitely try to answer those doubts in comments. Thank you.